Welcome everyone. This is Jim Chastain with EasyPower. I wanted to welcome everyone to our Thursday technical seminar. And before I introduce our guest speaker, who's going to be talking about the changes in industry standards affecting arc flash, we wanted to run a real quick poll question, and we appreciate your participation. And it pertains to the topics that are going to be discussed. So if you would please help us with some feedback, we would appreciate it. So the first is, how would you select switchgear? What criteria would you use to select switchgear protection when considering protective relays that sense both light and current? And if you would kind of indicate your preference or the criteria you would use. So here's how folks weighed in. And again, thank you for the feedback. The next question is, with the upcoming changes in 1584, what are your biggest concerns when you conduct an arc study? So this should be an interesting subject as well. So we appreciate your feedback here. And we're expecting very shortly the announcement of the release of the updated 1584. So this is very timely material and discussion to that point. Here's how people weighed in. So with that, I'd like to introduce Dave Durocher from the Eaton Corporation. And David, if you want to take it away, we're all ears.
Okay, thanks so much, Jim. I appreciate the opportunity to speak today and be a guest speaker on the EasyPower webinar. My name is Dave Durocher. I look after the global mining and metals industry for Eaton, and I'm a 38-year veteran of the company, and I'm involved in several of the IEEE code standards working groups, including the 1584. So I thought we do to just kind of go through an update here. I want to share with you the changes in the 1584 and also some of the things changing in the 70E and a few other standards around arc flash. And then we'll finish up with a brief case study of an installation in a industrial plant in Texas in the U.S. Where an arc flash solution was installed into vintage switchgear assembly. So I think most of us are familiar now that these are the key standards around arc flash standards. For sure, the NFPA 70E, which is really an electrical workplace safety standard. This standard is pretty rigorously updated. It last was updated this year. It's on a 3-year revision cycle, and it's a harmonized standard with the Canadian standard CSA Z462. I think there actually is a 2018 version of 462 out now, I believe. This, again, is a workplace safety standard. It's about what people do when they're working on or around energized equipment, and talks about recommendations for PPE and arc flash studies. The primary focus on the presentation today is the 1584. The 1584 first edition was introduced in 2002, so 16 years ago, and so this kind of came out in 2002 as a calculator. There was actually an Excel spreadsheet that came with it, and the whole essence of this standard, or actually it's a guide, IEEE guide, was to perform some arc flash calculations and create some data points on what heat energy measured in calories per centimeter squared outputs might be in the event of a 3-phase arc flash. And then the original guide actually just used a equation to model that heat energy. And as most of you know, this is the kind of the cornerstone for most of the software programs that offer short circuit coordination and arc flash study functionality. I mentioned again that I'm on the working group of the 1584. We've spent many years actually and trying to get more information around arc flash events. There's a very active group, over 100 people, including engineers from the software suppliers, EasyPower inclusive. And in July of 2017, there were over 1,000 comments that came back from the Revision 5 document. There was a ballot resolution committee that was formed, and actually in the IEEE standards world, each comment has to be actually responded to by this committee. That resulted in a Rev 6 of the working document, which has been sent along to the standards board and was approved by the standard board on 27 September. And so now it's really kind of in the cleanup stage. We expect, I think this year, I'm expecting December, maybe January, but we're expecting this year that the 1584 second edition will be published. Let's talk about some of the changes that are going to come up in the new 1584 and how that might impact specifically arc flash calculations. In the 2002 standard, there were about 300 tests that were performed. Since then, almost 2,000 tests have been performed, and there was great support from industry, a strong effort. There were over $3 million that were collected from industry participants, and there was these dollars were used to perform testing in high power labs. And one of the big changes or differentiators was a recognition that there's a electrode orientation model that needs to be reviewed. When the 2002 standard first came out, there were several engineers that came back and said, hey, what about if the electrodes are facing towards the person in the event of an arc flash? And so the decision was to take the first two configurations from 2002, which I've shown here in black text, vertical electrodes in a medical box, or VCB, and vertical electrodes in open air, VOA, and add to it three additional test configurations: vertical electrodes in a metal box with an insulating barrier, VCBB, horizontal electrodes in a metal box, HCB, and horizontal electrodes in open air, HOA. I'll go through each of these in this presentation and give you a feel for what this means. Note here that the group so far has not really, and in the scope of the new document, will not be included single phase calculations or calculations for DC systems. Let's have a look at some of these. I'll start off with the VCB configuration. There's a cartoon image here on the left, which is actually from the standard that just shows the electrodes, and all of these tests are performed in the same fashion. You basically take three phase conductors with a defined conductor spacing, and then you set up a small trigger wire and connect it between phases A, B, and C, energize the circuit, and intentionally create an arc plasma event. And you can see in the box in the center here that this is actually one of the test boxes that was used for the testing. And then in front of this box, a set of calorimeters is placed. And so the measurement of the heat energy is a direct result of the test. The vertical electrodes in a metal box, you can kind of envision the arc event first goes down, and then it kind of goes out towards the person in front of the enclosure. And there's a picture here at the right that shows a typical configuration. In this case, maybe a molded case breaker. You can see the load lugs. They're facing down. So that might be an example of a VCB configuration in the real world. The second configuration is the VCBB with an insulating barrier. And what was done here was just a recognition that, and you can see the test setup where we've got the conductors, and the conductors are actually lodged against a barrier. and the trigger wire is set up at the bottom of the electrodes. And so in this case, the arc event goes out, hits the barrier, and then again is reflected off and moves out of the box. So a little bit different configuration. I like this picture because you can see the calorimeters in the lower left of the image. And then the real world example might be a power circuit breaker. You can see, for instance, the line terminals of this breaker, where if there was an arc event, it would come down and it could terminate at the line terminals of the breaker itself, and the breaker being the insulating barrier. The open air configurations, both vertical and horizontal, probably more utility type of applications, not seen as much in industry, although there might be an outdoor switchyard as shown here in the upper image, where you could have open air conductors facing vertically, either up or down. And then I've got an image here for the horizontal open air, which might be, this shows a typical termination you'd see in, for instance, a pad mount transformer. So you would have the conductors facing out, and again, if there's an arc event, that would be an example of a HOA configuration. And finally, the last one, which is turning out to be, I think, the most contentious, so there's lots of discussion around this, was the horizontal electrodes in a metal box, HCB. Again, the image and an example. In this case, you might have there's certain designs of panel boards out where you can have a removable circuit breaker, and you might take the breaker out, and you can see in the remaining cell that you've got conductors that are facing directly outward from the enclosure. The thing that's most contentious about this is that in general, the horizontal configuration calculations come out higher. So a model was built for each of these 5 configurations. And interestingly, in the 2018 version, the vertical electrode calculations come out about the same, or in some cases slightly lower. But the horizontal are higher, could be a magnitude of up to maybe 2x higher. And so there's lots of conversations in the working group around what do we do, because we, in our experience over the last several years with the 2002 version, we've had calculations and determined incident energy, and people are not getting injured. So, it feels like we've got a pretty conservative model. But the horizontal model came out in most cases higher than the vertical. A couple other things that I think are noteworthy relative to the changes in the standard. One was one of the conversations around the 2002 edition was the bottom end. So there was a defined floor, that basically language that I've shown here, that just basically says equipment below 240 volt need not be considered unless it involves at least 125 kVA or larger transformer. So that provided power systems engineers a convenient floor where you could draw a line and say, hey, we're not going to model applications where we've got system MVA at 125 kVA and 240 volts. So this kind of presumed that the arc fault current wasn't going to be able to sustain itself at levels below that. The 2018 testing proved otherwise, and so it got a little bit more, it moved down the curve a little bit. You can see that there's basically language in there around 2,000 amp short circuit current and below. And so the language, and I've copied it from the guide, it says sustainable arcs are possible but less likely for circuits operating at 240 volts or less within available short circuit currents of 2,000 amps or less. So this somewhat draws a floor. But I've done some calculations here showing that for a given transformer at 240 volts, that comes down to about 115 full load amps, or maybe 50 kVA instead of 125. So the floor feels like it's moving a little bit lower. The likelihood of an event at 208 volts is fairly low, but in this case, I think this will kind of make the power system engineering world take another look at the bottom end and maybe choose a different place to stop modeling a system slightly lower than the 125 kVA and 240 volt line defined in the 2002 guide. A couple other things that are in the new standard. One is there's some voltage-based equations. There's actually two equations for 208 volt to 1 kV and another one from 1 kV to 15 kV. And in the 2018 edition, there's actually three different equations with a factor to allow for specific operating voltage. So you pick a voltage using the 2018 formulas. You might pick 600 volts for a 480 volt system. And then there is a allowance factor between the 600 volts and the 480 volts to correct for the actual operating voltage. There was in the 2002 edition, an enclosure size correction factor as well. As you can see from this table, that got a little bit more detailed, and there's more ratings and more enclosure sizes at given voltages. And so, again, a little bit more granular in terms of defining a specific application around the size of the enclosure. For sure, it's obvious on a larger enclosure because the arc is has more room to expand, that the energies are going to be different in larger enclosures than smaller ones. So interestingly, again, in the 2002 edition, for low voltage systems up through 1 kV, most of you are familiar that first you calculate an arcing current, and then you go back and you make another calculation based on 85% of the arcing current. The purpose for this was really to assure that if the arcing current was indeed lower than the calculated value, that did not specifically or significantly impact the protection. So you might have an overcurrent protective device like a circuit breaker, and if it was 85%, it's possible that given the trip curve of the breaker, you might move out of an instantaneous range and into an overload range, in which case maybe the clearing time would be different. So this was just a guide or a way to assure that if there was a lower arcing current, that the clearing time was accounted for, the change in clearing time. The 2018 edition actually has an interpolation factor based on the actual conditions. And so the calculation steps here are fairly rigorous in terms of coming up with an arcing current. There's first an intermediate average arcing current, and instant energy is calculated. And then there's a final arc short circuit current calculated. And then a minimum arcing short circuit current. And then there's the factors for the enclosure, for instance, are entered into the calculation. And then ultimately a final arcing current, incident energy, and arc flash boundary. So there's lots more data and lots more information I put down here at the bottom of this slide. It's much more sophisticated, probably good. It's more accurate based on actual test data. It's a little bit onerous. I think a lot of people will feel like, how are we going to go through all these calculations? And this is going to get much more complex. But fortunately, the key software suppliers, including EasyPower, are ready to go with this. As I mentioned before, they're all involved in the working group, so they have a good handle on these equations, and I think the software will be crunching most of the numbers. I've talked to some of them. There's a little different approach by each of them. I know that EasyPower's approach in the updated software will be to, as a default, to default to the vertical electrodes in a box. So, you know, they chose in this case to say, hey, we're going to go with, for the updated software, a default formula, and then make the power systems engineer choose to perhaps use a different one. So I'll update you on a couple of other standards that I think are relevant around arc flash. Again, we mentioned at the beginning the 70E. The big changes in the 70E over the last cycles are, one of the key changes is really the recognition and the differentiation between hazard and risk. When the 70E was first issued, we used to have language like hazard risk category 2 is equal to 8 calories, or hazard risk category 4 is equal to 40 calories, and that's the PPE that should be worn in that hazard risk category environment. Today, the standard, and even going back to the 2015 edition, the standard differentiates hazard and risk. Hazard is really the heat energy. It's, for instance, 6.7 calories per centimeter squared. And the hazard is either there or it's not. And then the risk is really more driven by the definition of both the likelihood and the severity of an incident occurring while someone is performing testing, troubleshooting, or energized work. So this talks about the likelihood of the occurrence, and if there was an occurrence, what's the potential severity. Most of you have seen and are familiar with the risk controls, starting at elimination and moving all the way down to the last line of defense, PPE. And the 70E is starting to incorporate language around some of these other specific areas. I think that will continue to expand. For instance, engineering controls is one area where I think there's a lot of focus in trying to reduce arc flash incident energy. A couple other things in the 70E worth noting. There's an issue around conditions of maintenance. If you read the language here, this is really saying that the owner is responsible to consider the manufacturer's instructions and recommendations along with the codes and standards. So there's a little bit more of a move towards recognizing that the recommendations of the manufacturer's equipment should be considered. There's a couple of exceptions in this updated 2018, which I like. This first one really says that it allows retaining labels if they were installed prior to the effective date of the standard, if the labels meet the requirements contained in the applicable standard that was in place when the labels were first put up. So this is good. This basically makes it so that every time there's a new edition of 70E, it doesn't mean you need to start all over. The second exception is unique to specific industrial supervised installations, and it basically allows the owner to not use labels if somewhere the calculations have been performed and that information is readily available to persons that would be performing service maintenance and troubleshooting. There's more rigor around the PPE. I think this is also a good move. There's a lot of PPE manufacturers, I think, are getting more and more credible. Early on, there were some less credible suppliers out there, but now there's a pretty good rigor around testing, and you can see that some of the requirements here in terms of labeling PPE with specific ARC rating, care instructions, model and serial number are now requirements in the 70E, which again I think is a good move. This is an interesting one here around electrical safety program equipment verification. So there's lots of antiquated equipment, vintage equipment installed in several facilities, and this really talks around newly installed or modified equipment to comply with applicable installation codes and standards prior to being placed in service. So, and there's some OSHA language. I've put a specific OSHA 1910 article here that talks about approved equipment. So based on testing by the manufacturer. So the notion here is that if you retrofit or upgrade equipment in the field, that you need to go back to the manufacturer and make sure that it's in compliance with some sort of standard. I have an example here at the bottom of this slide for medium voltage vacuum replacement switchgear. There's lots of different offerings out there in the market now where you might have an old Allis-Chalmers air brake medium voltage circuit breaker that's obsolete, no longer available. And several manufacturers make a vacuum roll-in replacement breaker that fits in that same cell. And they physically need to go out and buy that old Allis-Chalmers enclosure and test that breaker in that cell. And they test it to this specific IEEE standard that's called requirements for conversion of power switchgear. So one good example of testing a replacement product that goes into a vintage assembly to a standard. This one also is interesting. There's quite a few people that have installed voltage indicators in assemblies such as motor control centers where you've got a indicator that basically shows energized equipment, and you can see phase A, B, C, and ground current. The new 70E talks about a absence of voltage indicator. So there's specific language in here around having voltage indicators, and there are certain products available in the market today that include absence of voltage indication. So just like if you had your test meter, you know, the process to find and testing for voltage is to first take your meter and connect it to a known good voltage source, and then apply it to the specific test voltage that you intend to measure, and then bring it back to the known good source and test it again. So this is again an absence of voltage test, which again is a little bit different than several of the permanently mounted voltage detection devices that have been available on the market over the past several years. This one was interesting. There's actually language in there around the consideration of human error. I actually asked one of the people I know on this working group to give me a good example of this, because I thought, boy, this is pretty scary. How do we, anytime anyone's doing live work, there obviously humans are involved, and there's always a chance for human error. And the response I got, the example I thought was a good one, that said if for instance, a worker was in an energized cabinet, and there might be, in some conditions, energized conductors that are below the worker. So the incident of perhaps dropping a tool, you know, would have again, much higher risk than if the energized conductors were not at the feet of the worker. So I think, again, this is just recognizing, as I mentioned before, the hazard and risk, and in risk, what's the likelihood of occurring? Again, it's probably a lot higher if those energized conductors are at the feet of the worker. And also, what's the potential severity, which in this case might be very high. So again, just as part of the energized work plan, a consideration of human error was included in the 2018 update. The National Electrical Code, or the NFPA 70, is really an installation code for U.S. applications. And we're starting to see issues around arc flash energy creep into the NEC. The latest NEC document, the 2017, has some language in here, and it talks specifically about arc energy reduction for low voltage fuses and circuit breakers rated 1200 amps and higher. And so if you are a design engineer working on a specific new building or system, then according to the NEC, you need to consider engineering controls that would be, and there's 7 different options here: zone selective interlocking, differential relaying, energy reducing maintenance switches, energy reducing arc flash mitigation systems, and then a couple of different things on instantaneous trip settings, less than the arcing current or less than the available instantaneous override, less than the arcing current. So these are included in the NEC, and again, I think a move towards electrical workplace safety in an installation standard, which is, I think there's obviously a motion in that direction, and I think we all need to be aware when we're designing systems about what's in the NEC regarding arc flash. I'll talk about one more standard here, and before we jump into my specific case study, the ANSI IEEE C37.20.7 guide for testing metal enclosed switchgear rated up to 38 kV for internal arcing faults. Most of us are familiar with the original 2001 version of this. Arc resistant switchgear has been available in the North American markets for several years now, and most every manufacturer has an arc resistant design. I've shown here a image at the bottom on this slide of a specific lineup. This is a piece of 15 kV metal clad switchgear that's actually undergoing a arc test. This standard is really a test standard, and it defines testing engineered assemblies, power distribution and control assemblies based on an internal arcing event. And the premise or the basis of this standard is really to protect workers that are standing in front of or around the perimeter of a piece of switchgear or motor control assembly. Again, this, not unlike the arc flash testing in the 1584, there's a trigger wire that's defined in this test, and so you establish an arc event inside the enclosure. And the test standard requires that the arc event be redirected from the perimeter of the enclosure anywhere from the ground level up to 2 meters from ground, that it be redirected above that level. And in this case, the arc or heat energy is ejected via a top-mounted or roof-mounted plenum. You can see in this test, this is actual one of the arc tests from the C37.20.7. So this one's been around for a while. There's an update that just came out last year, and the big change in the update on the arc-resistant test standard is really in the scope. So there were historically only 3 different product groups that were included in the scope, and now there's an additional group of products that have been since added, and that includes metal enclosed bus, defined by IEEE C37.23, medium voltage controllers built to UL 347, low voltage motor control centers built to UL 845, switchboards built to UL 891, and also metal enclosed medium voltage air insulated circuit breakers for outdoor that are defined by this IEEE standard C3704. So the big change here is just more products are added and now can be tested to this arc resistant test standard. And the standard has changed quite a bit in that each one of these products has its own dedicated annex D through L. And so the test standard or the specific test setup for each of the different classes of products is defined in each one of these specific annexes. So you basically refer to the annex based on the product that is being tested. I've shown here at the left a table from the standard, and at the right an example of a certain product. This is actually a arc-resistant medium voltage motor control center. So this actually is one of the products in Annex I, and so if you refer to Annex I, there's different configurations of this assembly. I've shown here a Type 2B assembly. So the 2B design in the test standard requires that a compartment door might be open for a control compartment door, as we've shown here. And the arc is initiated in the enclosure, and even with this door open, the heat energy doesn't escape the enclosure. It instead is redirected up to the plenum at the top of the enclosure and exhausted 2 meters or above the floor. So this is just an example of one of those products. Again, I think a good move towards trying to add more products that are designed and also tested to this arc resistant standard. I'll jump over here and close out and chat about, I mentioned a case study. So one of the things that we've seen in our company is a lot of, after an arc flash calculation is done and a determination of what the incident energy is, there's a move towards trying to move people away from an application where they might need a 40-calorie suit that's shown in the picture on this slide at the left, and move towards a lower, for instance, an 8-calorie suit. So, is there a way to engineer the heat energy down or out, or move workers away from the energized equipment so that they're outside of the flash protection boundary? This is a case study of actually a cement plant in the Dallas, Texas area. Not unlike a lot of the industrial plants across North America. A lot of these plants were built in the 70s or before. And so although the business has a very strong health and safety management system in place, and they're focused on making sure that their employees are safe when working in electrical systems, the infrastructure is 70s vintage equipment, so there's not much opportunity to take advantage of some of the latest technologies that address arc flash hazards. In this plant, one of the biggest arc flash hazards, and probably most of you have seen the videos of arc events occurring in medium voltage, draw out, metal clad and metal enclosed switchgear. So most of the vacuum circuit breakers and medium voltage systems can be racked on and off in the bus, and in a lot of cases, industrial users will rack these breakers on and off an energized bus. You can see the image that I have here at the right is actually a picture of one of the workers in Eaton's factory where we manufacture this switchgear. And obviously he's standing in front of this breaker, racking the breaker off the bus with the door closed, but he didn't have any PPE on, and the reason he doesn't is that this enclosure is not energized. If it was energized, he'd be wearing something more like what these two workers are wearing in the bottom images at the right. And so, again, the vintage equipment is designed and tested, but not designed and tested to a arc test standard. And so in the event of an arc flash occurring while this breaker was being racked on or off of the energized bus, we really don't have any test data to prove that the door is going to withstand an arc event, or that arc energy is not going to escape from that enclosure. So a real problem, and again, this specific activity is one of the, I think, again, I mentioned hazard and risk. This is a very high risk activity, and it's an area where a lot of manufacturers are trying to focus and say, how can we move workers from outside of the flash protection boundary to do this type of work. I mentioned here, it says the door, closed door is not a protection, again, because vintage assemblies have not been tested to arc resistance standards. And so because there is no such test data, we don't really know what's going to happen with the door if there's an arc event. Lots of different alternative solutions available to support vintage equipment. I've shown a few here, including universal remote racking devices. Some cases there's a door mounted motor operator that can be connected, and then again, this just moves the operator away from the front of the enclosure while the breaker is being racked onto or off of the energized bus. There's an integral remote racking offering where there's a motor operator that actually fits inside the cell, and so the breaker kind of motorizes itself on and off the bus. And at the right, I've shown a typical medium voltage motor control center where there might be an isolation switch, and in this case there's a door mounted operator to open and close the isolation switch from a remote penance station, again moving the operator outside the flash protection boundary. This specifically, the specific cement plant decided that they had some vintage equipment that included a 5 kV medium voltage vacuum circuit breaker, and they used in this equipment, they actually had this function as a main circuit breaker and a lineup of medium voltage motor control. So this was used as a lockout point, a lockout tagout point for the motors that were fed by this motor control center. And so a decision was made to use this integral motorized operator and retrofit the cell assembly in the existing equipment with this integral motor operator design. And interestingly, a lot of the vintage equipment, the cell assembly and cell parts and the breakers are still the same today, and in this case the manufacturer was able to develop a offering that not only fits in the new equipment but also can be retrofitted into existing equipment. So this plant brought in a service organization to actually, during a scheduled cold outage, replace this cell assembly and put in a new motor operated cell. There's quite a bit of sophistication in this cell, these cell parts, and that there's individual limit switches, so you know where the breaker position is, connected, disconnected, or test position, so you know where the breaker is while it's being racked on or off of the bus. There's also a torque sensing functionality, so if in fact something might get jammed or stuck during the racking, then there's an alarm that goes off and the racking is ceased to exist. Here we really have a picture of a pendant station that's available. So there's a handheld pendant station where the operator can both open and close the circuit breaker remotely and also rack the breaker onto or off of the energized bus, connected, tested, and disconnected. And in this case, there's a picture of the updated switchgear. So again, now, anytime the breaker needs to be opened or closed or racked on or off of the bus, this pendant station can be used. I thought this was interesting. The engineer that was at the facility after this equipment was installed, he said, you know, this is a quote directly from the engineer. He said, the internal remote racking device upgrade on our 2 vacuum circuit breakers at the site solved 2 problems. First, most important, enabled our employees to remain outside the flash protection boundary when implementing plant lockout procedures prior to maintenance. Second, it eliminated the use of a portable remote racking device that had been hauled up and down the stairs from substation to substation. which presented another risk of injury to our employees during transportation. So a lot of electrical rooms are up on mezzanines and in places that are not that easy to get to. And these portable remote racking devices are only somewhat portable. And the opportunity to install this into the cell itself with a motor operator and just use a pennant station was a great improvement over the former operation. Of course, most of the new technology out there is communication ready, so this new cell parts, including the motor operator, communicates via Modbus, and there's a COM port. And so this allows you to get the information relative to this, the circuit breaker racking up onto a touch screen. There's a standardized HMI that's shown here in the upper left. And the switchgear can be set up, and the HMI can be modeled from a kiosk or wall-mounted enclosure or on the switchgear. And then all of this information is able to be put up onto the DCS system in the specific plant or up in the cloud. And so there's lots of functionality here in the new equipment that can be applied to the vintage assemblies by advent of this upgrade. So we'll save a few minutes here for questions at the end. I'll just kind of finish up with some conclusions and just recommend that all of the people on this call push to continue to be updated and familiar with what's happening on industry standards around arc flash. The fact that you took the time to attend this session, and I know that there's been some other webinars on this topic, it's a good thing. I think it's important for all of us to make sure that we know what's happening and changing codes, standards, and guides around arc flash events. I think it's important to understand arc flash hazards and how people interact with energized equipment, with specifically the 1584 changes. If you give some thought to what you might do in performing an arc flash calculation or study, probably the data collection is going to change. Now we're considering the orientation of electrodes and enclosure sizes. So again, I think knowledge around the standards is going to impact the way that the studies are completed and how people interact with energized equipment. I think the issue around manual racking of medium voltage breakers is quickly becoming obsolete. I think people are going to need to decide to either rack them on or off a de-energized bus, or come up with some solution like the one that we mentioned here, where the equipment is retrofitted so that the breaker can be safely racked on and off the bus without an operator in front of the gear. There's a lot of standards around lock, tag, and try. Some of these I think need to be reviewed as some of these new technologies come out. And this last point probably would require another webinar, but I've been involved in some of the standards around 61508, which is a functional safety standard for safety integrity level SIL systems. And I think that this integral racking functionality that I showed you here is maybe a piece of that puzzle. It's an opportunity to move towards functional safety and possibly remote isolation, where isolation of electrical systems can be accomplished remotely. And so I think there's going to be lots of headroom moving forward, and lots of opportunity for new applications around electrical safety, driven by not only the standard, but also some of the new products available from manufacturers that produce products to support a safe workplace environment. So that's it. I finished a few minutes early. Hopefully we'll get a chance to field a few questions. Jim, I'll turn it back to you.
All right. Great job, David. Thank you. Here's a question from Richard Reese, and it's an intriguing suggestion. He says, even though 70E waives the need to reanalyze with each new edition of the standard, will the 1584 second edition take precedence? For example, will past studies need to be revisited to assess equipment with HCB bus orientations? He says it seems like not doing so puts personnel at greater risk and leaves the owner open to increased liability. How would you answer that?
That is an intriguing one. I think I guess my view on that is that when we're talking about electrical workplace safety and PPE and working on or around energized equipment, then the 70E I think would really take precedence there. The 1584 is really just a calculator. It's a way to calculate and determine what the incident energy is. An owner might decide to be prudent. An industrial plant might say, I think that with the 1584 changing, I want to update my study and put up new labels based on what we now know. But I think the 70E, which really is kind of about the labels and working around energized equipment, and its language that talks to if you did the study based on the current standards and guides that were in place, it's okay to keep those until your 5-year review comes up. I think I'd probably bet on that taking precedence.
All right. I do have one request to see if you would release copies of the presentation to the audience.
Sure. I'm not sure mechanically how to do that. If I can do that through
we can actually do that.
EasyPower,
yeah, we can do that with the link on the webinar. So we'll be releasing a notice for both the recorded video link and then a copy of the presentation that you've provided. It looks like that's the extent of the questions. Again, thank you very much, David, for an excellent job. And I know for myself, it gave me a lot of good insight and answered questions I already had just from reading through the material from the updated release. So I think it was beneficial for all.
Okay, I appreciate the opportunity to present on the EasyPower webinar today. Thanks.
Thanks to everyone for attending, and we look forward to having you visit us again somewhere down the road. Have a good day.